Hai, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ada Faisal bin Muhammad Faisal. I'm from BMKA S21 and from Group D. We'll start presenting the topic of reducing drag coefficient of an Ahmed body using ANSYS Fluent. So I will start the introduction. The Ahmed body is a simple model used to study car aerodynamics. Created in the 1980s by Professor Ahmed, it looks like the back end of a car with a sloped surface and flat edge. Its shape helps researchers understand how air flow around vehicles. This module is important because it shows key airflow behavior like flow separation and vortex shading, which affect drag and lift. Studying these effects help engineers design cars that perform better and use less fuel. In summary, the Ahmed body is a useful tool for testing and improving car designs. Its simple shape makes it easy to study how it moves, helping create more aerodynamic and efficient vehicles. So now I will present about the problem statement topics, which is this project focus on reducing the drag of the Ahmed body using computer simulation in ANSYS Fluent. The goal is to study how air flows around the module, find ways to improve it, and test those changes through simulation. Only no physical models or real world testing will be done. Although the project gives useful experience with an SIS Fluent, it won't cover every part of vehicle aerodynamic or use advanced optimization methods. It's meant to help students learn basic aerodynamic concepts and how to use simulation tools within a limited time and with available resources. The main aim is to improve aerodynamic efficiency by lowering drag while keeping enough downforce for stability. Lower drag means better fuel economy and fewer emissions, which helps improve vehicle performance and support sustainability in modern car design. Okay, now we jump to the part objective. First, to utilize ANSYS Fluent software to conduct computational fluid dynamics (CFD) simulations for optimizing the aerodynamic of an Ahmed body. Second, reduce the drag coefficient of the Ahmed body through iterative modification and simulation. Third, gain proficiency in navigating ANSYS Fluent, setting up CFD simulations, and interpreting simulation results. Fourth, understand the significance of the drag coefficient in vehicle aerodynamics and its impact on vehicle performance and fuel efficiency. Fifth, identify effective modification for reducing drag and improving aerodynamic performance.
Hi, my name is Navindran Kaladharan. My matrix number is B0922103661, and now I'm going to talk about literature review that we done for our project. Okay, next I'm going to talk about Hammett body in vehicle aerodynamics. The Hammett body created by S.R. Hammett in 1984 is a basic car-like shape used to study airflow around a vehicle. It has simple box design with slanted rear end, similar to the back of the real car. The model helps researchers understand how air moves around a vehicle, especially how air separates from the surface form verticals behind the vehicle. These verticals create a force called pressure drag, which increases the vehicle's resistance to motion. The angle of the slant rear part is very important because it changes how the air behaves and how much drag is created. By changing the slant angle and the shape of the back, researchers can see how the airflow change and how the drag coefficient is affected. Because of this, the hammered body is often used as a standard model to test improve and aerodynamic design for vehicle. Drag coefficients and its important. The drag coefficient CD is a value that shows how much resistance a vehicle faces when moving through air. In car design, lowering the CD is important to improve fuel efficiency, reduce carbon emission, and boost vehicle performance. The total drag comes from two parts, pressure drag and viscous drag. For shapes like the helmet body, pressure drag is the main factor. When CD is lower, the vehicle uses less energy to move, especially at high speed where air resistance is strongest. Because of this, engineers often use computer simulation and wheel tunnel tests to change the vehicle shape and reduce drag during the design stage. Computational Fluid Dynamics (CFD) and ANSYS Fluid. Computational fluid dynamics is a powerful tool used in engineers to study how fluids move around objects. It helps engineers see and measure airflow without needing to build physical models. One popular CFD software is ANSYS Fluid, known for being accurate and flexible. It is widely used to study different types of fluid flow. In this project, ANSYS Fluent is used to simulate how air moves around the helmet body. It helps analyze speed, pressure, and vortex patterns. It- with this information, engineers can find areas that cause high drag and suggest changes to reduce it. Past research on helmet body optimization. Many researchers have studied ways to reduce drag on the helmet body. Some common methods include vortex generators, changing the rear slant angle, adding base cavities, using diffusers, adding spoilers or splitter plates. The small shape change can reduce the drag confidence CD by 5% to 20%. Using CFD simulation is repeated step called iterative optimization has also been shown to help improve designs and make them more aerodynamic.
Assalamualaikum. My name is Wan Rafizul Mizan, and I will explain about the model setup boundary condition of this Ahmed body. The first one is the meshing process, where we meshing the grid analysis when we doing the uh, grid analysis of the ANSYS. The next one is ANSYS simulation process, where we find the coefficient drag, the coefficient pressure, and anything that flows through the Ahmed body. Next, we go to the result, which is the post-processing result of the CD, CP, and counter plot of velocity and pressure. As we can see, the first result is the benchmark, which is the unmodified Ahmed body. As we get the drag coefficient is 0.35553, and the velocity magnitude have 79.599 meter per second, and it have static pressure of minimum negative 2349.080, and its maximum. We also got pressure coefficient of 0.859 the maximum, and the minimum of negative 0.5919, and turbulence for this benchmark. So this is the force, lift force, and movement force of the graph, and this is the streamline for the benchmark Ahmed body. The next one is the result of the modified of Ahmed body result. The first one is the CP of the modified Ahmed body, which is we got the maximum 0.9343 and the minimum negative 0.5905. So this is the graph of the drag force, lift force, and moment force against the iteration from the graph. And the next one is the streamline of this figure. Then we go to the comparison result. As we can see, both of the benchmark and the modified have same number of element, which is 2.5 million, but both of it have different drag coefficient, which is the modified one have the lowest drag coefficient, which is 0.33824, and the velocity magnitude also, the modified one have the smallest value, which is 79.465, and the benchmark have 79.599. And the static pressure, also the modified uh, have more less than the benchmark one, and the the CP also, but in the CP, the modified result have more higher pressure coefficient than the benchmark one, which is the modified have the 0.9343 for pressure coefficient and have for maximum, and have negative 0.5905 for the minimum. So this is the graph of the benchmark and the modified Ahmed body, the graph for coefficient pressure versus the Z, which is the position.
Good day, my name is Kishore Kumar. My matrix number is B0922101131. So I'll be presenting about the discussion, model comparison and evolution and conclusion. Okay, firstly, the mesh refinement and boundary conditions. The first step in the optimization process was mesh refinement to stimulate how air flows around the Ahmed body. The model was imported into HyperMesh as a STP file, then checked and scaled to the correct size. Getting the scale right is important because the wrong size can give inaccurate results. Next, a detailed mesh was created using an element size of 0.02, resulting in 2.5 million elements. This fine mesh helps capture important airflow details, especially in areas with turbulence or flow separation. The AutoMesh feature in HyperMesh was used to evenly spread the mesh across the model. And lastly, boundary condition was set for the simulation. The air enters the model at 52 millisecond inlet velocity and exits through a pressure outlet. These settings are important to make the simulation behave like a real airflow situation. Okay, next I will talk about the shape modification. After refining the mesh and setting the boundary conditions, changes were made to the armored body shape to reduce drag and improve airflow. The original armored body has a flat rear and sharp angles that causes air to separate the create turbulence, increasing drag. To fix this, the rear slant was smoothed out to help the air stay attached to the surface. The design may have include features like diffusers or other shapes to guide airflow more smoothly, especially at the back and the bottom of the model. These changes aim to improve the wake region, the turbulent area behind the body, and reduce the swirling air vortices that adds to drag. A more streamlined shape helps the airflow better, which reduce drag and improve performance. Okay, next I will talk about the optimization approach. The optimization focused on improving the armored body shape step by step to get better aerodynamic results. This was done through several simulation runs, with each one aiming to reduce drag and improve airflow. The first simulation used the modified shape and improve important values like drag coefficient, pressure, and airflow speed were checked. Based on these results, small changes were made to the shape, such as adjusting the rear angle to reduce turbulence and keep the airflow attached to the surface. After each simulation, the results were reviewed and the shape was updated. This repeated process helped gradually improve the design. In the end, the drag coefficient was reduced from 0.35553 to 0.33824, showing a clear improvement in aerodynamic performance.
Hello guys,
My name is Muhammad Shazam Suhaimi. Now I will talk about comparison of benchmark and modified Ahmad body. Now comparing the original benchmark and modified Ahmad body shows that the change have improved aerodynamic performance. The key results include the drag coefficient and velocity magnitude. The drag coefficient dropped from 0.3553 to 0.33824, a 5.1% reduction at that. This shows that the shape change light smoothing helped the reduce drag, which improve fuel efficiency and vehicle performance. Next is a value for the velocity magnitude. The highest airflow decreased slightly from 79.599 mm per second to 79.465 mm per second. This small drop means the airflow is smoother than no less turbulent around the modified body, which help reduce the drag. Okay, next for the comparison of benchmark body and modified MR body. For the static pressure, the maximum pressure decreased slightly from 1706 to the 1695 Pascal, and the minimum pressure become more negative 2349 Pascal to 2559 Pascal. This change suggests better airflow control, the less flow separation help reduce drag. And for the pressure coefficient, the maximum coefficient increased from 0.8 952 to 0.9343, showing the improved pressure distribution in the surface. This means the airflow stays smoother and more stable, contributing to the lower drag. Okay, next, for the turbulence level dropped from 258.878 to 156. Lower turbulence means smoother airflow and less resistance, which also helps reduce drag. Overall, the modification made the Ahmad body more aerodynamic and efficient. And for the evolution and modification, the change made the Ahmad body were successful in reducing drag by smoothing the rear slant. The air flow improved, creating smaller vertical and smaller wake behind the drag body. This helped the airflow attach longer and reduce turbulence, leading to the lower drag. The 4.1% drop in drag coefficient is a good result. Other change in airflow speed, pressure, and turbulence also show that the modification improved the aerodynamics. This shows that even small design change can make a big difference in fuel efficiency and overall performance. Although the results are positive, more improvement could be made by continuing to refine the shape, possibly focusing on other force like this study shows that how useful CFD and simulation are for testing and improving design without reading physical models, saving both time and cost. Okay, and finally, and lastly is a conclusion. This study aimed to reduce the drag of the Ahmad body using Ennis fluid or CFD computational fluid dynamics. The model was improved by smoothing the rear slant and sharp edge to help airflow to move more smoothly. This just reduced the drag coefficient from 0.35553 to 0.33824, showing that the shape optimization can improve the aerodynamic. Or the result showed improvement. The airflow stayed smooth, the pressure distribution improved with higher pressure coefficient, which is 0.9343, and turbulence dropped from 258.878 to 156.020. This means the flow around the body become more stable and efficient. In conclusion, even small shape changes made through CFD simulation can greatly improve aerodynamic performance. This method can be applied to real vehicle design to boost fuel efficiency and performance. Further refinement could lead to even better results. Okay, that's all from us. Thank you.